eigenvectors. Okay. So there are two types of matrices I want to look at. One is called Vandermonde matrix. Okay. And the other one is called circular matrix. Okay. Yeah, these two matrices have very interesting and special properties as follow. So first, let's take a look at Vandermonde matrix. Okay, let's represent this matrix as M. Okay. So, what is a Vandermonde matrix? A Vandermonde matrix is a matrix that is a square matrix. So it has the size of n by n, okay, square. For example, if we have a M matrix of 2 by 2, okay, it can be written as something like this: 1, lambda 1, 1, lambda 2, okay. These lambda, uh, they are not the eigenvalues, okay. So lambda I, lambda j can be any numbers, can be any number, okay. And please note that they are not equal to eigenvalue, okay. So for this type of Vandermonde matrix, if we find the determinant, okay, we will find that it is just 1 multiplied with lambda 2 minus 1 multiplied with lambda 1, okay. So this is the for the size 2 by 2. If we have a 3 by 3, this Vandermonde matrix will have this form. Okay, so the first column is all 1. Second column is lambda 1, lambda 2, lambda 3. If you don't like this lambda, you can put some other letters like L, okay, or M even, yeah. And the third column is going to be lambda 1 squared, lambda 2 squared, and lambda 3 squared, okay. Okay, so let me put it here again. Uh, you can change this variable to like mi, mj if you want, okay? Just in case you get confused. So if you compute this, you'll find that the determinant of this Vandermonde matrix 3 by 3, it has a special form, which is the lambda 3 minus lambda 2 multiply with lambda 2 minus lambda 1 and multiply with lambda 3 minus lambda 1. Okay. So it's quite interesting. Okay. So similarly, if you expand this Vandermonde matrix all the way to the size of n by n, so you get something like this: matrix m by n. It is equal to 1, 1, 1, lambda 1, lambda 2, lambda 3, all the way to lambda n, and so on. So you can sort of guess, what it looks like. Lambda 3, all the way to lambda n square. And then it goes all the way to lambda 1 to the minus 1, lambda 2 to the n minus 1, and all the way to lambda n to the n minus 1, okay? And the determinant of this matrix is going to be lambda j minus lambda I, and then it's a product, it's a multiplication where j is greater than I, okay, and I is greater than equals to 1. Oh, sorry, this is lambda I minus lambda j. Okay. You can use MATLAB to test whether it's true or not. Okay, and j has to be less than or equal to n. Okay, so that's the first matrix, which sometimes come up. When you look at some work. Number two, it is one also interesting. Number two, let me go to the next page. Okay, just so that it's easy to see. Number two is the circular matrix. Okay, so what is a circular matrix? Circular matrix is a matrix where, so let me call it as a, okay, let's call A. A is fine. A circular matrix is a matrix where if you have one row as say H0, H1, H2, the second row is going to be shifted of the first row. So if you shift this thing to the right, you have H2, H0, H1. And then if you shift these to the right, you get H1, H2, and H0. Okay. So this is the shifted to the right or to the left. Actually it's to the right. Shifted to the right. So it's the first row shifted to the right. Okay. And this one is the second row shifted to the right as well. Okay. So why is this an interesting matrix? So we can take a look. So first of all, if I multiply this A matrix with 1, 1, 1, okay, what do I get? Pure. If I multiply A with 1, 1, 1 like this, what do I get? So this one has a dimension of 3 by 3. This one has a dimension of 3 by 1, right?
Yes.
So I will get 3 by
3 by
1,
1
right?
metric.
Okay.
Yes.
So what do I get as the first row if I multiply A with 1, 1, 1 like this?
It's a H1. Yeah, sorry. H0 plus H1 plus H2.
Okay. How about the second row?
Second row is H2 plus H0 plus H1.
Okay, which is the same thing, right?
Yes.
Right. And then the third row,
It's also the same thing.
yes. Okay. So I can write this as H0, H1, H0 plus H1 plus H2 and multiply with 1, 1, 1, right?
Yes.
Okay. So you see that this looks like a lambda. I don't know. This is like a eigenvector, and this is like a lambda 1. So, right? So it has a very interesting form. So 2. So now I multiply A with 1 omega and then omega squared. Okay. Where I let omega to be e to the j 2 pi over 3, which is cosine 2 pi over 3 plus j sine which is cosine of uh, 2 pi over 3 plus j sine of 2 pi over 3. Okay. Oops. Uh-huh. Did I quit it? Let's do again. Okay. Okay. So if I multiply A with 1 omega and omega square, what do I get? Thanatson. So I get the same thing, right? Okay. 3 by 1. What do I get for the first row?
S0
Yes.
S0 time omega.
Okay. I multiply first
H1
row,
H1 H1.
right?
Sorry.
H1 is okay.
H
Omega, and
H2
then
time omega
H2
square.
omega squared. Okay. How about second row,
The same.
which is H2 plus, right? H0,
H1 omega.
H0
Oh,
omega
okay.
plus
H1
H1
omega square.
omega squared. And the last line, by the same approach,
H1
we get H1
H2 omega and H0 omega square.
and H0 omega squared. Okay. So here what I can do is I can write these as, so I write first row, I can write it as H0 plus H1 omega plus H2 omega squared. Okay. And I can multiply this with 1 omega squared as well. Okay. The reason I write it like this is because if you take a look, so if I multiply this to the first row, here 1, I get this correct, right? If I multiply this row with omega, so I will get, what is it? H0 omega plus H1 omega squared, right? And then plus H2 omega to the fourth. Okay. So you notice that if I multiply here, I get this. Wait, did I do something wrong? H0 plus H1 omega plus omega to the fourth. So I get H omega. Do something wrong. Okay, so let's see. So if I write it like this, I get, so first row I get it correct, right? H2 omega squared. For second row, I have H2 plus, here I have H2 plus H0 omega, and then I have H1 omega square. Okay. And what did I do wrong? And then the last one, I have H2 omega to the fourth. Okay. But because omega is e to the j 2 pi over 3, so uh, sorry. So H2 multiply with H2 omega square plus multiply with omega, right? So this line comes from this whole thing multiply 1. So I get this. This is correct. So second line comes from this row multiply with omega. So for H2, I get omega cubed. Sorry. Just many numbers. Okay. But because omega, let me erase it so that it's not so confusing. Okay. Okay. So because second line, I have to multiply h2 omega square with with omega. So I get h2 omega cubed, right? But because omega is e to the j 2 pi over 3, so omega cubed is e to the j 2 pi, right? Which is equal to cosine of 2 pi plus j or j sine of 2 pi, which is in effect, it is equal to 1. Okay. So it means this term becomes 1. I can just write as h2. So it's the same as this line. I have h2 plus h0 omega plus h1 omega square. Okay. Similarly, if I multiply these with omega square, this row, then I will get h0 omega square plus h1 omega cubed plus s2 omega to the fourth. Okay. And we can use this same approach. Uh, h, h, h0 omega square is the same here. h1 omega cube becomes h1. Okay. h2 multiplied with omega to the fourth. This one is h2 omega cube multiplied by omega. This is 1. So I have h2 omega. Okay. So in for part 2 here, it means that if I multiply a with this the eigenvector numbers 2, I get this as, I can express as lambda 2 multiplied with eigenvectors number 2. Okay. And uh, and similarly, I'm not going to prove more. And similarly, if I multiply a with 1 omega square and omega, okay, I'm going to be able to write it as another lambda called lambda 3 and multiplied with multiply with 1 omega omega square and omega. Okay. So that means for any circular matrix, in general, we can write from the expression earlier in terms of matrices. Okay. So for example, for the 3 by 3, which is H0, H1, and H2, and then H2, H0, H1, and then H1, H2, and H0. Okay. We can multiply with the eigenvectors, which is 1, 1, 1, 1 omega, omega squared, 1 omega square, and omega. This will be equal to 1, 1, 1, 1 omega, omega squared, 1 omega square, and omega, and multiply with all the 3 lambda. Okay. So this is the diagonal matrix. So all the non-diagonal elements, they are zeros. Okay. And it's very interesting that if we have A and B, okay, which are circulant matrix, okay, we will find that both A and B have the same eigenvalues and also the same eigenvectors. Okay. Okay, where we let omega to be e to the j 2 pi over whatever dimension we are looking at. Okay. So it's very interesting property. So in some system where you have a circular matrix, you can exploit this type of this type of how do you call it properties. Okay, so before we go to the next one, so let's take a look at one more matrix, okay? And this one will be used in the singular value decomposition, okay? This one is called unitary matrix. It's a very simple matrix, actually. Let's represent it as a U, okay? So for the unitary matrix, there are some properties involved with unitary matrix. One is all the columns of matrix U are orthogonals, are pairwise orthogonals. Pairwise orthogonal means that any two pairs, any two columns are orthogonals. Any two columns are orthogonals. Okay. Secondly, the column of matrix U, each column has a unit length. Okay, meaning that the element in each column, when you square and then sum them together, you get 1. Okay. And number 3 is that unitary matrix, if you transpose and multiply with itself, it will be equal to identity matrix. Okay. Lastly, number 4, for unitary matrix, lambda is equal to 1. Okay. And what are some possible metrics that are unitary metrics? If you remember, you've seen before, right? We learned about one matrix that if you multiply the transpose is the inverse of itself. So an example is permutation matrix. Okay. Okay, so this is called a unitary matrix. For example, if you take a look at 3 by 3, like this, okay, you find that each column, any two columns, they are orthogonal or independent in a way, right? Also, each column also has unit length, okay? That's second property. For the property number 3, we learned this already, okay? And lastly, if you find the lambda, you get that is 1. Another possible unitary matrix is like this. Let's say U is equal to cosine theta minus sine theta, and cosine theta. Okay. So this one also, any two columns are orthogonal, and each column has a unit length as well. H, for example, another one, you can, this is also a unitary matrix. Okay, it's a Hadamard matrix in communication. Each column represent like a code, for different users that are orthogonal to each other. Okay, so this is one of them. Okay, and to wrap it up of the unitary matrix, one last important property of the unitary matrix is property number 5. Okay, the unitary matrix, when you use it in any system, it will preserve length. Okay, in terms of inner product, when we apply inner product of okay, so let's take a look. What does it mean? It means that, let's say that given that we have inner products of one vectors to another vectors. Okay. If I multiply this unitary matrix to each vectors, okay, then what I will get is the y transpose u transpose times u times x transpose. But these two from the property number 3, it is just the identity matrix. So I get y transpose multiplied with x. Okay. So it means that sometimes when we have a system that you multiply vectors together, like convolution or projection, okay, if we try to, if sometimes we can multiply with this unitary matrix in order to solve something easier, and it will not change the size. Okay, so last topic, let's take a look at the singular value decomposition that we are supposed to talk about today. So singular value decomposition is a very interesting decomposition. Okay, if you look on the internet or any textbook, it is often called SVD. And it is used in so many areas of work, because matrix analysis is used in engineering, it is used in social science, it's used in science, it is used in finance, it is used in AI, and so on. Okay, so singular value decomposition is often used, but how is it different from the decomposition that we saw earlier today? So for singular value decomposition, it is used to decompose a matrix A that doesn't have to be square matrix. Okay, so A no need to be square matrix. Okay, so previously we look at square matrix, right? And then we find the eigenvalue and also the eigenvectors, and then we can decompose in terms of the eigenvectors and also the eigenvalue matrix, right? But singular value decomposition goes further in the sense that you can decompose any matrix that doesn't have to be square matrix in a way. Okay, and how do you decompose it? So a matrix with the size of m by n can be written as a matrix U, which is m by m multiply with the diagonal matrix with the size of m multiply m by n, and then multiply with the V, which is with the size of n by n. Okay. So the form is still quite similar to what we saw earlier, but in this case, it is the dimension here of the eigenvalue is not a square matrix anymore. Okay. And to decompose A in terms of this matrix U, lambda, and also V, okay, so U and V, they are unitary matrix. Okay, so U transpose multiply U is equal to U multiply with U transpose is equal to identity matrix. But this will be equals to identity matrix of size M. And for the V transpose multiply with V is equal to V multiply with the V transpose. This will be equal to identity matrix, but with the dimension n. Okay, or m by m and then n by n. So they're different. Okay. And additionally, in order to find U is the eigenvectors of A times A transpose. Okay. So this one has the dimension, the size of M by M. Okay. V is the eigenvector, but on the other hand of A transpose multiplied with A, which has the dimension of N by N. Okay. And lastly, for the lambda with the dimension of M by N. Okay. So this is eigenvalue matrix of lambda 1, lambda 2, all the way to lambda m. Okay. And then all 0. Okay. Where we order it, lambda 1 is greater than or equals to lambda 2, greater than or equals to lambda 3, and etc. Okay. So we order from maximum to minimum. Okay. So that's how we do. And it turns out that this lambda I, it will be eigenvalues of A times A transpose or A transpose times A. Both of these will give you the same eigenvalues. Okay. So let's take a look at an example, and then so we understand what we are talking about. So for example, let's say that we are given a matrix A. Let's say it is equals to 1, 0, 1, 0, 0, 1, 0, 1. Okay. For simplicity. Okay. So in order to find the V, okay, so we will multiply A transpose to A, and this will be equals to 1, 0, 1, 1, 0, 0, 1, 0, 1, and multiply with 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. So this is the 4 by 2. This is 2 by 4. So I'll get a 4 by 4 matrix, right? Okay. And so, okay, let me just compute it. Okay, you can check it later. So I'll get something like 1, 0, 1, 0, 0, 1, 0, 1, and then repeat 1, 0, 1, 0, 0, 1, 0, 1. Okay. So we will try to find the eigenvectors of this A transpose times A, and then we can find the eigenvectors V for the unitary matrix V. Okay. So for this matrix, if you compute it, the method using the previous method that we learned, okay, we will find that we have lambda as 4 of them, which is 0, 0, 2, 2. Okay. And using the same previous method, you will find that these eigenvectors for each eigenvalue, so the 2 of them are the same, right? So you get 4 columns. Okay. And but because they have some free variables, so I will choose the values so that they are orthogonal. So I choose 1, 0, 1, 0, 0, 1, 0, 1. And then for eigenvalues of 2, I can choose something like this. And then I choose the one that orthogonal. Okay. Because they have free variables, so we can do this. So this V is not you can choose. Okay. And similarly, so let's call this as part I. Okay. So this is what we get as V. And similarly, for U, we can multiply A times A transpose. Okay. And here you will get a smaller size of matrix. In this case, it's 2002. Okay. Maybe I don't go in so detail. Okay. But you get to do this when you do homework. Okay. And it turns out that for this part, the lambda is equals to 2, 2. And the U matrix is m by m, right? So which is 2 by 2. So I get as 1001. Okay. So it means that this A can, you notice that this column has unit length already. So no need to normalize it. So here we find that this A can be written as the, let me see what it is. Is it U transpose? U multiply with the eigenvalue matrix, U transpose, right? So here I can have U multiply with eigenvalue matrix and then V transpose, okay? So U is the 1001 and the eigenvalue vectors is it will have the size, because A had the size of 2 by 4, 2 by 4, right? So this thing has a 2 by 4 as well. Eigenvalue vector. This is 2 by 2. Okay. And for the V has a size of 4 by 4. Okay. So for the V, this is simple. We can just do a V transpose. So we get each row to be each column. So 1, 0 minus 1, 0. Second row we have 0, 1, 0, 1. And third row we have 1, 0, 1, 0, 0, 1, 0 minus 1. And then 1 over square root I put out here. And for lambda, because lambda has the actually only 2 value, so we have 2, 2. Okay. And so the remaining ones we don't use. Okay. So we can write it like this. Even though A is not a square matrix, we can decompose this way. Okay. And yeah, so today we learn how to decompose matrix, whether they are square matrix or they are non-square matrix. And we utilize the concept of eigenvalues and eigenvectors. Okay. So you find that SVD is used in many systems. For example, in some communication system, that has input X, and it has like a multi-antenna system called MIMO. Okay. And then on the receive side, you have a Y. Okay. Then normally the system in here is a two-dimensional system. We can call A. It's a huge matrix. Sometimes in some system, this A matrix can be like hundreds times hundreds, or hundreds or thousand times thousands. Okay. It doesn't have to be square matrix. Okay. So you find that Y is equals to AX. Okay. And if you want to find what X is, okay, what can you do? Okay. If the system is quite constant or quite stationary, it doesn't change value so often. Okay. So it means that in order to find X, in order to find X, you need to find if A is a square matrix, then if A is a square matrix, then you can just say that X is equal to A inverse and times Y, right? If this is square, okay. If it's not square, then you cannot just do inverse like that, okay. but you can approach other ways. So that means that we need to find the inverse often. Need to find inverse often. Okay. So if we write A, it can be square matrix. You can write it as the S multiplied with this and S inverse. Okay. So we can find that the A inverse is S and then eigenvalue matrix inverse and then S, right? And then I think it's S inverse, right? Yeah. Okay. So that's one way. But if you express A, because you said that we cannot find A inverse, but if we can express A as, how do you say it? U multiplied by eigenvalue vectors and then U and then V transpose. Okay. Then what you can do is you can uh, you can uh, you can do it like this. So you can multiply A transpose. Okay. So if A is not square, okay, then Y is equal to AX. You can multiply A transpose to the front. So you get A transpose times A and then X, okay? And so this X is equals to A transpose times A inverse times A transpose times Y. So remember that this A transpose times A, it can be huge. It's not like a small matrix. No? It can be 1,000, size of the 1,000. It can be even millions. Think about like a very huge matrix. So what we can do is, if we write A transpose times A's, what do we get? We get V times these times U transpose, right? And A is U, these, and then V transpose, okay? So this thing become identity. So you will have V times eigenvalue vectors square times V transpose. Okay. And if you need to find an inverse, okay, so it's simple. So if you have A transpose times A is equals to V times eigenvalue vector square times V transpose. If you want to find inverse, okay, this is just V times this square, V transpose inverse, okay, which is V multiplied by inverse multiplied by V transpose, okay. So meaning that we can uh, find an inverse easily with by using these, okay. And when you make circuit or FPGA or something like that, it is much easier to compute this way. Okay, you have small number of circuits involved. Okay, yeah. So this is the uh, singular value decomposition. Okay, you have any question? Okay, maybe next time we will give some additional example. So we have 2 more lectures. Okay, I think so. You can stop the recording now. It's already almost